All right, so we're very happy to have Erik Carlsson from UC Davis back for lecture 2 on a combinatorial formula for the nabla operator. As Anna mentioned, I'm in Vail, Colorado in the Rocky Mountains. So anyway, go ahead, Erik.
All right. So let's see. So last time, I was explaining this formula. And so the formula stated, so this is the main formula from that paper. And so nabla is the nabla operator in the x variables. And this is this plothistic substitution where I substitute 2n sets of variables minus x and minus y. And nabla is interpreted as acting on the x variables. And the statement was this was this complicated sum from before. And I think I want to explain what all these things meant again. That x to the a, y to the b. And so this is the main formula from that paper, combinatorial formula for the nabla operator by me and Anton. And so where I finished last time is I was explaining that how to interpret this thing as the Frobenius character of a certain module. Call this MK. And just for simplicity, I'm just using k equals 1 to illustrate. And so what this MK was is it's defined as the image of a certain map, which we'll call pi, where pi is the map that takes a polynomial in 4n variables. Sorry, so x1, little x1 through little xn, little y1 through little yn. Same for the others. Totally unrelated to capital X and capital Y, just totally different set of variables. Into the free module of rank n factorial over just the x and y variables. And I'll call the basis vectors E sub sigma. And the map pi is defined by pi of f is equal to the sum over all sigma in Sn of f of, I'll just write this as x bar, y bar. Then I evaluate the z and w variables at the x and y variables, but reordered according to sigma. Okay. So I have this map. I have the ring and foreign variables. I have the map of CXY modules, which sends f to the sum over all permutations of this particular coefficient just in the x and y variables. So let's just say map of CXY modules. And then M is defined as the image of this map. And so M, which is the image of pi, is a doubly graded Sn cross Sn module. And so the by grading here is all the x's and all the y's get the same, all the x's get the same degree. We'll grade those by q. The y's all get the same degree. We'll grade those by t. The first Sn action is determined by tau of fx y e sigma. is equal to fx tau y tau e tau times sigma. This is the first factor. And then the second factor, you would sort of think of as a right action. And so I'll use a different letter, which is star. And this is defined similarly, except it doesn't act internally on the variables. It just sort of multiplies on the right by tau. And so I'm calling these dot and star. Because in the geometric picture I'm going to show you with Springer fibers, these would correspond to what are called, so this is using Alan Knudsen and Juliana Timoshko's terminology of dot and star. And so the star is what one would call the Springer action on the space I'm going to explain. And the dot is also something sometimes called the monodromy action. But for now, in terms of this module, it's just an algebraic thing. Okay, and so now what I'm saying is, right, so what I've just given you here is it's infinite dimensional, doubly graded SN cross SN module. And so anytime I have a graded representation of the symmetric group, I can take its Frobenius character. Since I have two different commuting SN actions, what I really get is a symmetric function in two different sets of variables. And so these are X and Y, and the two gradings are Q and T. And so this statement here is that this equals the Frobenius character of this sort of explicit module that I just described. So in the setup, the X variables correspond to the star, and the Y variables correspond to dot, the way we set it up. And now what I'm going to do is explain what this has to do with geometry. So first of all, maybe any questions about just the definition here of this space? Okay, so what I was saying before is that M, this is in fact exactly this. So this is a polygraph type module of exactly the same type that would appear in Mark Heyman's papers. But under this dictionary, so in the dictionary of that paper, the polygraph is sort of the output of, you input a coherent sheaf on the Hilbert scheme of endpoints on C2. And in this case, the sheaf that this corresponds to is the Purchase bundle tensor with itself. And if I put a K here, then there would be also copies of this of the tautological line bundle on the Hilbert scheme. So this is a polygraph type module. And so now what I'm going to explain is a different interpretation in terms of homology of Springer fibers of a particular type called a GKM space, which is one which has an explicit algebraic presentation. And in fact, that's where this this formula comes from. Is it comes from counting Schubert varieties in that space. Okay, so first off, let me start with sort of a warm-up example. So let's take kind of a simpler version of pi. And let's imagine I have just the X and Z variables. So I take the exact same map, it's still into the direct sum over all permutations of f of x bar times E sigma. And the map is defined defined exactly the same way. So pi of f is equal to the sum of f of x bar, and then x bar with the labels reordered. And so I claim, so this is sort of a simpler version of the statement I want, is that the image of this guy, which is just a CX module, is isomorphic to the equivariant cohomology of the usual flag variety, complex flag variety. Okay, so what's going on with that? So the nice thing about this setup is, so I'm saying this is isomorphic to this equivariant cohomology ring, but also this equivariant cohomology ring is so the flag variety is an example of a Goreski-Kottwitz-McPherson space, and so what that means is that it's equivariant cohomology and usual cohomology have an explicit algebraic presentation, which is what I'm going to use. And so here's how that goes. So a GKM space, let's say I have a torus, let's say it's a d-dimensional torus, and it's acting on a smooth algebraic variety. Let's see. For instance, the flag variety. So it's called a GKM space if three things are true. So first of all, the set of all fixed points is a finite set. So in the case of the flag variety, it is a finite set. That set is in correspondence with the symmetric group. And so that is the same reason that we're, it's the same reason we're seeing this term here. So more generally, these, the E sigma, those correspond to the fixed points. Two, the set of one-dimensional T orbits is finite. And three, X is equivariantly formal. So the top two are both, geometric conditions. Three is more of a technical assumption. And so what this means, equivariantly formal, is it means that a certain spectral sequence degenerates. That's really the definition. But there's a lot of properties X might have that imply equivariant formality. So the definition is that a certain spectral sequence degenerates. But the property of being equivariantly formal would be implied, for instance, by the statement that there's no odd homology So this would be implied by the statement that X has no odd cohomology groups. And also when I say cohomology groups, I mean usual cohomology, not equivariant cohomology. So it is possible for a space to have only even dimensional equivariant cohomology groups and not be equivariantly formal. These spaces actually come up. So the statement here, it's no odd usual non-equivariant cohomology. And so now a theorem is that if we have such a space, then we have an explicit presentation of its equivariant cohomology, and from that I can also obtain its usual cohomology. So if x comma t, that's right, is GKM, then equivariant cohomology group of X is equal to the set. So via the map, right? So if X is a space, it has a torus action. The fixed point set is finite. That was the assumption. Then I have an inclusion map. Taking the disjoint union. Taking the set of fixed points, which is just a discrete set, into X. Therefore, I get a pullback map on equivariant cohomology, right? So this is the pullback map takes HT star of X into HT star of the fixed point set. The fixed point set is just a union of a bunch of points. And so the right thing is the same thing as the direct sum over all the fixed points of HT star of a point. And this in turn is equal to the direct sum over all P and XT of the equivariant cohomology of a point, which is just a polynomial algebra. And the number of variables is there's one variable for each generator of T. U is C star. And so now the statement is that via this map, I can describe explicitly the equivariant cohomology of X by its image. And that image is the set of all elements of the form sum over P with the property that with the property that, let's see, I should have said something first here. So if the orbits of X are all one-dimensional, so the one-dimensional orbits all look like C star. And so their closures are all just going to be CP1s. And so the endpoints, right? So the endpoints of each of the different CP1s, you might call these the north and south pole. So I'll call these P and Q. Next T. And so now the condition that describes the image is its all elements with the property that Fp minus Fq is congruent to 0 mod alpha, where alpha is the weight of the action of the torus on the tangent bundle at P to CP1, which is the same as negative the weight of the torus acting Q at CP1. Okay, so I'll give an example in a sec with the flag variety. Maybe I'll stop here. Any questions about this, about the theorem? Okay, so example.
So one question.
Yeah.
So you're there's no technical things with like the fact that you're working with an infinite dimensional space, is there?
Oh, you mean for the next I mean, well, this guy's not like, you mean that
like X in your case is an in variety rather than a variety. That doesn't, I guess because you have odd cohomology vanishing, then everything's fine.
Oh, well, so yeah, so okay, yeah, so skipping ahead. So the would-be space, the Springer fiber that corresponds to the M from above. So in fact, yeah, this is not exactly GKM space because it's going to violate condition 1. And so the answer is that you just,
right.
You know, just like what you usually do, you write it as a union of Schubert varieties, and each Schubert variety is GKM.
Right. Okay.
So yeah. So let's see. Yeah, so to give an example, so let's go back to the flag variety. So if X is equal to the flag variety, which is equal to GLN mod B, the torus is equal to C star to the N. And the action comes from the just the inclusion of the torus in GLN. So in this case, the fixed point set is equal to the symmetric group thought of as permutation matrices. So these are the torus fixed flags. And so we have an orbit which looks like C star, and its closure connects two fixed points, sigma and tau, if tau equals some transposition multiplied on the left by sigma. So this is the criteria. So I can ask if I have this, so the fixed point set is the set of all permutations. I can ask for which pairs of permutation is there a one-dimensional T orbit, which is a C star, whose closure contains those 2 points as the north and south endpoints. And the criteria is exactly when there exists a transposition, not a simple transposition, just any transposition swapping I and J, multiplying sigma on the left to get tau. And so in this case, the weight of the torus acting on the tangent space is equal to xi minus xj. Okay, so therefore, m, which is equal to ht star FLN, is equal to the module over Cx, which is the set of all sums of this form with the property that f sigma minus f tau is a multiple of x1 xi minus xj, oops, I should say, is congruent to 0 mod xi minus xj. In other words, it's a multiple of xi minus xj if sigma equals the transposition Sij times tau. And so this is an explicit module. Okay, so I'm just going to list a couple properties and then I'll show you how to generate these classes on a computer. I think it's kind of useful to see, and then I'll explain what this has to do with the module M that I wrote down above. So the first thing is the ring structure. It's just given by some f sigma times e sigma. And this is equal to the sum f sigma g sigma. So in other words, multiplication is just pointwise. So it's the same as the ring structure would be on just the disjoint union of a bunch of fixed points. Two, if x has a T equivariant CW decomposition, which means I can write x is the disjoint union a bunch of spaces, each one of which is just affine space. So it's just like c to the power of the dimension of each one. So this is what I have, right? So in the case where x is the flag variety, this is the decomposition of x into Schubert varieties, or sorry, Schubert cells, closures being the Schubert varieties. Then this gives us a basis. Of ht star of x as a module over C of x bar. So 3, even if we don't, if x is a GKM space, we always have that ht star of x is free. So in the, right, so we always have that ht star of x is free over the x variables. But if we happen to have a T equivariant CW composition, then we get an explicit basis that generates that thing as a free module. But whenever X is a GKM space, this is always free over CX. And in fact, the usual cohomology of X is isomorphic to the equivariant cohomology of X, tensored over C of X with just C, where C is equal to the vector space C thought of as a module over the X variables in which all the X's act trivially. So it's this guy modulo the ideal generated by those X's. So in particular, I can recover the usual cohomology from the equivariant cohomology. Okay, so then fourth thing, and then I'll show you calculation. Do with Poincare duality. And so the statement is the equivariant Borel-Moore homology is equal to the dual vector space of the cohomology. Regarded, oops. Regarded as a C subspace of the field of rational functions in those X variables. So maybe I'll, well, let me return to this in a sec, actually. And so this is equal to the equivariant Borel-Moore homology. This is actually quite important. So the equivariant Borel-Moore homology. So this is the homology group that comes up in equivariant intersection theory. Okay, so I might return to this statement later, but right now, let me just show you an example of computing one of these cohomology rings. So
should the, wait, before you switch,
yeah,
did you mean to write usual cohomology there, or was it equivariant cohomology?
Oh wait, let's see. Usual. Let me change back. Let's see, where did I say usual? Oh, no, I meant to say, yeah.
Oh, okay. things.
Okay, so now I'm going to show you as an example of, so on a computer, I want to calculate the equivariant cohomology of the flag variety. So here's a little computer software. So a reference for how to compute these things on a computer. I'm going to refer to, there's a paper by Juliana Timoshko, and I should write this on the board in a sec, which is called Permutation Actions on Equivariant Cohomology. And also Alan Knutson's paper, which is here. Yeah, Grubner geometry of Schubert polynomials. But here's a particular implementation that's done in Maple. And so what I've done here is I've just generated a little module which encodes HT star of the flag variety for n is equal to 3. Okay, and so what it outputs using those same kind of methods is, so that uses the variable q here instead of what I was calling e. And so what it outputs is the bases generated by the Schubert cells. Okay, so what I get if I input some permutation and I ask for the corresponding generator is I get a linear combination of permutations which are greater than the input one in the Baruha order. And this set of generators is actually uniquely determined by the fact that the only non-zero coefficients are greater than, say, 2, 1, 3, and that they satisfy the GKM relations. So you can recursively build them that way. So to give you another example, let's say I took 2, 3, 1, and I multiplied by the transposition S13, which would be this guy. I would get 2, 3, 1. So I'm going to give you an example of how you I'm going to show you that the GKM relation is satisfied. So if I take the module and I subtract these two guys, and then I factor I factor the terms. Oops. Sorry, I wrote the wrong thing here. I'm supposed to find that this is a multiple. I subtract these now. Let's see. Sorry, guys. Something's up with my script here. Why is this not working? This last night, I'm supposed to be obtaining that this is a multiple of T13. Hmm. Yeah, I'm sorry, guys. I ran this last night and I looked at it and it factorized properly. Why is this not working? Okay, well, let's see. So what I'm supposed to be getting right now is that if I subtract, okay, I think I'm gonna have to write up a thing for this later. I'm totally baffled right now. This is supposed to factor. So I'm supposed to subtract these two things. And what I'm supposed to get is something that's a multiple of x1 minus x3. I think maybe I'm going to have to write up a little note and explain what was supposed to be happening here because something's wrong. It's not producing the right thing right now. But so the statement is, what I'm supposed to be obtaining is a collection of polynomials. Sorry. Yeah, I'm sorry. I said this totally backwards. So here's a particular basis element. I'm going to check that this particular basis element is in that module. So if I look at the coefficient of this guy in front of Q of 2, 1, 3, I get x1 minus x2. And so now if I take 3, 2, 1 multiplied by 2, 1, 3 on the left, I get 2, 3, 1. And so now, so therefore what I have to get is that I take the coefficient in front of F1 of Q of 2, 3, 1 minus the coefficient in front of F1 of Q of 2, 1, 3. I will in fact get something which is a multiple of x1 minus x3, and that is 0. Also, if I take the coefficient, in front of 2, 3, 1, that's going to be 2, 1, 3. And so this, the next relation would tell me that if I take the coefficient in front of 3, 1, 2, and subtract from that the coefficient of 2, 1, 3, I'm also going to get a multiple of x1 minus x3. And in this case, I'm also getting 0. Yeah, I'm sorry, guys. Totally, I'm kind of screwing this up here. But what I'm saying here is that if I take the coefficient of any one of the polynomials of this F1, and I subtract from that the product of that thing with a transposition Sij, I'm always going to get a multiple of x1 minus x3. And so what these classes are is, so these are the equivariant versions of the Schubert classes. And so if I use the ring structure to multiply these guys and express these back in terms of the basis, I can recover structure constants for Schubert polynomials. Maybe I can send us notes. Yeah, I think I should probably do that for sure. Okay, so let me go back to the board here. And I want to say what the space is that corresponds to this formula. So now in this paper, so the module M is equal to the image, the map pi, taking xz into the direct sum over all sigma in the symmetric group of C of x times E of sigma. And so I'm saying M is the same thing as the equivariant cohomology of the flag variety that I just described. And so the identification is that so in order to describe this, what I'll give you is there's an action. So there's a map from C of xz into HT star of the flag variety. And this then maps into the direct sum of C of x times E sigma. And so this the composite of these two maps is pi. And so what this first map is that C of x acts on HT star of the flag variety. Just because this thing is explicitly described as a module over C of x. The z variables act on the homology by multiplication by Chern classes. In other words, zi is equal to C1 of the line bundle Li, where Li is the line bundle, which is the ith flag modulo the I minus first flag. And so this map is you simply multiply the identity, multiply x and z to 1. And the composed map, this is the module describing M. So because HT star of the flag variety is generated by multiplication by Chern classes, and this map is injective, I can describe HT star of the flag variety as the image of C of xz in the direct sum over sigma of C of x bar times E sigma. And so this is the meaning of the map pi. And so now coming back to this. Yeah.
What do you mean by multiply by 1? What is 1 here?
So 1 is the element, it's 1 in cohomology, which is equal to just the sum over all sigma of just E sigma.
Oh, okay. Mm-hmm.
And so I multiply these by x's and z's in the sense of generating.
Right. Okay. So like f in each coordinate.
So like f in, yeah, exactly. So yeah, so 1 in cohomology is just the sum of all those fixed points, which does satisfy the GKM relation. And so it's just generated by multiplying all these guys by 1. And it's the same module as M. Okay, so now what I'm saying is that this thing that I described before, so this is actually the same exact kind of space. So if I took out Y and W, what I'm giving you is a presentation of the cohomology of the flag variety. And so what I'm saying is that in the bigger case, this thing which describes the nabla operator, this is also the same exact type of presentation, but for a different space. And so the first thing you might guess is that probably X and Y are the torus variables. And so I'm about to give you some space with fixed points also given by permutations and with a 2n dimensional torus. In fact, that's not the case. So what I am going to give you instead is it's a space with still an n-dimensional torus. But now the fixed points, I'm going to realize as the direct sum over all compositions A in z greater than or equal to 0 to the n of just Cx bar times y to the power of A times E sigma. And so what I'm really going to give you is a space with still just an n-dimensional torus, but whose fixed points are given by pairs of a non-negative integer vector and a usual permutation. And so another way to say this is that this is a direct sum over the semi-direct product of Zn greater than or equal to 0 with the symmetric group Sn. And so what I'm giving you is a space whose fixed point set is in bijection with affine permutations, but which are positive. Right? So usual affine permutations are this guy. And so this is a space whose fixed point set is in bijection with just those subset of affine permutations, which are positive in the translation component, non-negative.
Question. In this direct sum, could you interchange X and Y?
In this direct sum, I could interchange. No, what I could do is I could interchange Y and W. So I could write this like this. A and Z greater than or equal to 0. C of X and then E sigma and then W to the power of A. And so this would be kind of like the semi-direct product, but on the right.
Thank you.
But actually, maybe you're also asking because this is also symmetric in the X and Y variables. And so the answer is I can simultaneously interchange X and Y and Z and W in the original description I gave you of this module. But that description is totally opaque when I write this as the homology group of something. So I could have started by switching those in the beginning. But the homology totally obfuscates permuting those variables, which is basically a version of the QT symmetry. So as usual, like with the formulas, that ends up being obfuscated. Okay, so here's the space I'm going to describe. And now I have to decide how much I say now, and maybe I should leave some for last time since I lost some time with the computer. So do I stop like right at an hour, or do I go over like 5 minutes?
I think you can go over, sure.
Okay, thanks. So the idea is, here's the space I'm gonna this relates to. So the space is called the unramified affine Springer fiber. In type A. And so maybe I'll just write down the space, and then I'll say what the connection is with these formulas. So first of all, we have the usual space, which is the affine flag variety. And so what this is, so this is the affine version of the flag variety. And so this is G, which is GLN, with coefficients in the set of formal Laurent series in a variable T, modulo GLN with coefficients in the ring of formal power series. Say the affine. This is what's called the affine Grassmannian. And then what I have is a second space. So this is the affine flag variety, which is G with coefficients in the formal power series. Let's see, was there a... modulo, it's called the Iwahori subgroup. And so what this subgroup is it's the inverse of the map G of T goes to G of 0 of the map, which takes G with coefficients in the ring of formal power series and evaluates at T equals 0. So this just maps to G. And so Y, right? So this description, this is what's usually the affine Grassmannian, the flag variety version. So this is the affine flag variety. Is similar, but we've replaced G with the ring of formal power series with the inverse of that map of a set of upward triangular matrices. The affine Springer fiber is a finite dimensional but not compact version of the usual Springer fiber, which is the set, all those orbits, G times I, the property that G inverse times gamma times G is an element of the Lie algebra of I. So generally, a subset of this form is a type of affine Springer fiber. And the particular one that corresponds to this module M is the one where my input matrix is a diagonal matrix times the power of T. And so now, saying that the fixed point set with respect to the n-dimensional torus. The fixed point set of this variety with respect to the n-dimensional torus, which is just the usual torus sitting in G, which is a subgroup of G with coefficients in the ring of formal power series. The fixed point set is in fact the entire affine Weyl group. And so the variety with the fixed point set describing M is one which I'm going to call Y plus. And so really what this is, the simplest way to describe it is it's just the union over all Schubert varieties corresponding to affine permutations, which have positive, which have only positive translation elements. So the statement, which I can say, is that the nabla operator applied to this element is equal to the Frobenius character of the equivariant homology of this space. So this theorem, so this is actually from a follow-up paper, also with Anton. And the way the proof goes is, on the one hand, from the first paper, the nabla operator of En applied to this plathistically transformed En is equal to this combinatorial sum. On the other hand, this combinatorial sum is equal to the Frobenius character of the equivariant so the equality is verified by showing that this the expression that's on the right-hand side of the main theorem is in fact the same thing you get if you count Schubert varieties in Y of gamma K. Okay, so maybe I'll just say 2 minutes here. So, so this is a combinatorial count. And a proof of this statement, so we give 2 different proofs. So this is the statement from that paper, a combinatorial formula for the nabla operator. And there's 2 different proofs. So the first proof is one that's just totally, it's totally combinatorial. And so what we do is we take the expression gamma K, So in other words, take the candidate for this, the candidate formula that we're trying to prove for the nabla operator, applied to En, statistically transformed En, and I show that if I take that thing and I evaluate at y minus, at q minus 1, I get something which is triangular in the x and y variables. So in other words, A0 mu lambda of qt equals 0 unless mu is less than or equal to nu in the dominance order. So basically, this is the thing that would have to be true, right? Because nabla is triangular in the Macdonald basis. So since the non-modified Macdonald polynomials are triangular, right? They're defined by axioms, being triangular and having the same leading term in the Bruja order. We do the same sort of argument that appears in the paper, the combinatorial formula for the Macdonald polynomial. And we just sort of verify that this satisfies the axioms and everything sort of vanishes. So the second proof is based on a method developed by Anton. And it's in the paper, which is character varieties, Poincare polynomial of character varieties. And also, Macdonald polynomials and Springer fibers. So this is more of a geometric argument. And in fact, it's the same exact kind of geometry as with these, the exact same type of geometry. You can see the Springer fiber in the title that we've got here. But it's not so easy to connect the two. So both the combinatorial proof. So I mean, I think he might be able to say much, say more than me about how this argument relates, this combinatorial argument and the geometry that we've, the geometry that connects these two spaces. But at the moment, they're kind of sort of separate. So I think there's more to say there. Okay, so maybe I'm kind of over here. So yeah, sorry, I was a little sorry for the screw up with the code there. So maybe I should type up some notes, and there is so there's more I wanted to explain. Actually, I kind of didn't get there. So I don't know, is a third talk a good idea, or?
I think it'd be a real good idea. Yeah, Thursday is open if that works for you.
Yeah, that'd be great.
Okay, well, let's thank Erik. And any questions for him? And we'll have another talk on Thursday.
Nice talk, Erik.
I have a question.
Go ahead.
Sorry, I'm not sure. How is there a way to relate the because the cohomology of the flag variety is like the quotient of a polynomial ring with this representation using the T version with the E sigmas, if that makes sense what I'm saying.
With the E sigmas, sorry. So which version with the T? So T being like the T variable.
Oh, I meant T as in the torus action, that the HT star versus just an H star, where I think of as the quotient by polynomials by elementaries.
Yeah, I kind of totally ran out of time there. That was one of the points I wanted to say there. So yeah, so the answer is yes. So so let's take this. God, the screen is freezing too. So the question is, if I take this map and I take the image of this guy, the question is, how do I relate this to the fact that the cohomology of this thing, the usual cohomology of the flag variety is the co-invariant ideal, which is polynomials and variables modulo the elementary symmetric functions. I think that was the question.
Yeah, that's right.
Yeah, so the statement is that the kernel of pi. So the way I can write pi, so I can explain the action of x and z in this fixed point basis. So it's very simple. If I take zi times e sigma, this is equal to x sigma I times e sigma. Right, so that describes and then xi of e sigma is just xi times e sigma. So the kernel of the map pi is actually the ideal in the 2n variables, which is generated by ek of the x's minus ek of the z's. See, because if I take any symmetric polynomial in the z's and I multiply e sigma by it, right? So all it does is it's the same as multiplying that same symmetric polynomial in the x's, because all that multiplying by e sigma does is it changes the order of the x variables. And so in fact, this is exactly the kernel of the map pi. And so if I set the x variables to 0, I get the usual generators for the coinvariance.
Nice. Thank you. Cool.
So the affine Springer fiber you're doing is these unramified, is the unramified version.
Mhm.
And Hikita's was like the ramified, and he had a nil elliptic operator. Is there any kind of direct geometric connection between the two with can you degenerate one to the other somehow?
I kind of think no, it's sort of it's different. I think they're two sort of different presentations, because so Hikita's setup, so in Hikita's setup, so it's the same sort of thing, like the combinatorial formula for nabla of En. This is a sum of Schubert varieties in a different affine Springer fiber, like one that's very closely related, but it's the Springer fiber associated to, I mean, it's really n comma n plus 1 parking functions, right? Which is actually the same as n parking functions. But so in that case, the matrix gamma is it's like this guy. All to the power of n plus 1. So like there's, yeah, these weird, facts which are true, which is that drn is equal to that module m that I was describing. And I tensor over this guy with C. But this is, in terms of cohomology, this is sort of not, this is not like this tensor product has an interpretation in cohomology, but it's not as this n plus 1 comma n Springer fiber. It's in terms of this sort of interesting quotient by this unramified Springer fiber by a lattice. So I kind of think they're different. This is it's sort of an n plus 1 kind of thing, whereas this is an n comma n sort of thing. Like I'm sure there's a way to say why they're the same, but yeah, they're very closely related, but sort of n plus 1 instead of n comma n. If that makes any sense.
Sure.
Okay. Any other questions? So I actually have a question. Bit tangential to what you're talking about, but related. So Marino, Alessandro, Francois, and I have a recent preprint where we study a generalization of the nabla operator, which involves two sets of variables. So you let x and y be sets of variables. You define nabla y applied to a modified Macdonald in x as the product of that modified Macdonald in x and the same one in y. And then we conjecture that if you apply nabla y to en of x, it's sure positive in both sets of variables. And it's kind of, I think you can get it from Anton's scheme where he has these multiple sets of variables. If you start with 3 sets of variables, say x, y, and z, and then let z be 1 minus q, 1 minus m. I mean, 1 minus q, 1 minus t. I'm just wondering if there's any geometric meaning for as a module for nabla y of en of x, because I know in your first talk you had these modules where it had a double S in action.
Yes. Let's see. So does it look like this, or is it
Yes. Well, nabla sub y of h mu of x is h mu of x times h mu of y. So in a way, your nabla, and if you take the coefficient of s1 to the n of y, it becomes nabla.
let's see. It is, I should be writing h tilde mu of x here.
Yes,
And
yes, right. Yeah.
but let's see. I don't. So it's nabla y of h mu of. So where did y
X.
go?
Yeah, equals h mu of x times h mu twiddle of x times h mu twiddle of y.
Oh, this is my definition of.
Yeah,
So
that's
I'm
the
defining
definition.
an operator to be. Oh, okay, I see. So I'm defining kind of nabla sub y to be the thing that multiplies h mu of x by just adding a different variable, basically.
Right. And then we want to ask, why is nabla sub y en of x sure positive in both sets of variables? That's the conjecture.
Let's see. Well, let's see. So I guess this is kind of like I mean, the Cauchy product is like if I took En of x, just x over 1 minus q 1 minus t, then nabla y, this would be
I think that might be the same. Wait, no.
Yeah.
Right.
This is right.
I think this would be correct, right?
Yes.
So
Yes.
and so, but then the statement is, oh, interesting. So in other words, so now, but how do I just get En?
Well,
can-
one
So,
thing you could do is take nabla y of that bottom line, nabla z, say, of that bottom line,
yeah.
and then let z be the, just replace z by 1 minus q times 1 minus t. And that would kind of, I think that would be equivalent to nabla y En of x.
So I think an equivalent way of saying is you can have the sum of h mu x, h mu y, h mu at 1 minus q, 1 minus t over the w mu, the
Yeah, right. That's maybe a better way to say it.
Let's see. I want to say something like, I mean, normal nabla commutes with nabla y. And so
Right. Yeah.
like, I want to say something like, I want to take plethism of 1 minus q, 1 minus t outside of everything. And then like, I want to get this guy from that. So wait, would this not be, yeah, can't I say that nabla y, let's see. I want to say this is nabla y, and then nabla 1 minus q 1 minus t of En of x. Right, so I'm kind of using the same notation here, just for a general like thing that's being plethismed.
Right. Right.
And then can't I go like this of nabla of so am I actually not, well, let's see, writing it this way though, it looks like we're just getting,
it'd be without the second nabla.
yeah, sorry. So it seems like one, well, yeah, so it seems like this would be, yeah, maybe it's a specialization of, well, now it's puzzling me a bit here, as this seems like, oh, wait, but this is a 2 variable thing. Yeah, maybe it's, I mean, maybe it's related to, well, actually, wait, is it sure positive or is it signed sure positive?
Well, we're using the original nabla with no sign. So,
yeah, I mean, like, is
yeah.
it sure positive
But
or
it
is
is
it,
sure. It's sure
Yeah.
positive. Yeah.
so it's, there's not with the sign thing that comes up in the sign positivity guide.
No.
It's actually
No.
not in either variable. There's nothing like that there.
Right.
Yeah, maybe it might be special. Maybe it's I I mean, if I've written this correctly, it seems like it's the character of M and then 1 minus Q, 1 minus T.
Aha.
Um, actually, that kind of surprises me that it's sure positive, though. I would have thought there'd be. Yeah, I guess I would have thought there'd be signs. I would have thought it'd be sign positive. So there must be something a little off, but yeah, it's possible it's related. Like it looks like the way it's written down, like there should be a way of looking at that formula, in relation to M. I mean, I think this is kind of right, isn't it?
Yeah, I think that's one way to write it. So anyway, maybe this is a little involved, and we can just maybe I'll ask you an email or something.
Right.
Okay. So I guess we should stop the recording, and